So let's look at more examples of more complex predicates and matching of indexes. Let's say we are given a hash index on A and a hash index on B, and the predicate is A equals 7 or B equals 5. So in this case, do either of these indexes match this predicate? The answer is no, because this is already in CNF. This is one unit within that CNF, one conjunct. Okay, so you can, there's only one conjunct in CNF over here, and the hash index on A, even though it can be used for A equals 7, the set of RIDs that satisfy B less than 5, you have no clue about them. The hash index cannot help you with that. Okay, so that means you will end up doing file scan anyway to get the records that match B less than 5. Might as well do a full file scan and skip the hash index as well. Okay, so that's why the index does not match. It doesn't help anything with reducing the I/O cost. Hash index on B is useless because this is anyway a less than, plus there's a disjunction in this conjunct over here. So this index cannot tell you anything about A, and so you cannot do anything about that. Okay, so here is an example of a predicate, and index is not matching this predicate. This predicate has a disjunction inside. Another example, let's say there's a hash index on A and a clustered B plus tree index on B, and the predicate now has two conjuncts. Okay, so there's A equals 7 and B less than 5. Which index matches this predicate? So how many of you think the hash index on A matches this predicate? Raise your hand. How many of you think the hash index on A does not match this predicate? How many of you think the clustered B plus tree index on B matches this predicate? And how many of you think it does not match? The answer is both of them match, because A equals 7, equality predicate in this conjunct over here, hash index, so it's a primary conjunct. B less than 5, clustered B plus tree on B, so this matches this conjunct, it's a primary conjunct. These two are non-overlapping parts of the predicate. You can use both of them, intersect the RIDs, and you will get the records that satisfy the whole predicate. Okay? So in this case, both of the given indexes match this particular predicate. Finally, let's look at another complex example. Given a hash index on A, clustered B plus tree index on B, and this is your conjunctive predicate. A equals 7 or C greater than 10 and B less than 5. So the first question to ask is this Boolean expression in conjunctive normal form? How many of you think yes? How many of you think no? The rest are still processing? Yes, do you have a question? Well, the answer is yes. It is in conjunctive normal form. Why? Those who raised hands for yes. Why? Yes? Yep. You have an AND mediating two subpredicates, and these subpredicates only have a disjunction in them, or they are atomic. Okay, so this is conjunctive normal form. If you have a disjunctive normal form, you can rewrite this into A equals 7 and B less than 5 as one subpredicate, and then OR mediates C greater than 10 and B less than 5. Okay, so this predicate is already in conjunctive normal form. You have two of these subpredicates that are either atomic or they have only disjunctions mediated by ANDs. Okay, so now given this, does the hash index on A match this predicate? How many of you think yes? How many of you think no? The answer is no. That's correct. What about the clustered B plus tree index on B? Does that match this predicate? Raise your hand if you think yes. What about no? The answer is yes. Because this is a primary conjunct, B less than 5 can match this. This does not match this conjunct at all, because C greater than 10, the hash index can tell you nothing about that. Okay, so the hash index cannot help here, and only the B plus tree index can help here. And so only the B plus tree index on B matches this predicate. Okay? Is that clear? Yes, question?
Question in the second one.
Yeah.
If you didn't have the hash index on A, you could still use the B plus tree index on B.
This one?
Yes.
Yes, that is correct. Even if there is no hash index on A, you just have the cluster B plus tree index on B, it still matches this predicate and you can still use it. Because it matches this conjunct over here, and so that's a primary conjunct, so it matches the whole predicate.
If it were or and you only had a B plus tree, then no.
If it was an OR over here, and you have a B plus tree, the hash index clearly does not match.
Well, let's say you don't have that.
If you don't have a hash index at all, if you have only OR and only the B plus tree index, the B plus tree index alone will not match. Because you have an OR, the B plus tree index can tell you nothing about A equals 7. You will end up doing a file scan anyway. Okay, so similar situation as this. You can replace this hash index with a B plus tree index. It will not match this predicate either. Okay? Okay, that's a good question. Any other questions? Now you know what sort of indexes match what sort of predicates. So this is how, as a select implementation, you can choose an indexed access path based on how much you're reducing the I/O cost and the runtime compared to a sequential scan. So that's a wrap on how do you do select in a scalable manner and also with high runtime efficiency, high performance at scale. Because these index structures are secondary storage aware, they can index even petabytes of data, even though you have only gigabytes of memory. These index structures can reduce your I/O costs dramatically by orders of magnitude. Okay, so that's how you have effectively implemented your selection with the selection condition to get only as much of the matching records as possible. I mean, actually, all of the matching records and a superset of that, and ignore the rest and not retrieve them into memory at all. Okay, next we move on to the project operator in relational algebra. Okay, so recall that we talked about this dichotomy in relational algebra. Project is deduplicating by definition because relational algebra deals with sets. In the extended relational algebra, there's a version called the bag algebra where relations are bags or multi-sets of tuples. There, you can explicitly state, is your project deduplicating or not? So first, if your project is not deduplicating, that's equivalent to your select clause in SQL, where you just have this attribute list, and you give the table. That's a non-deduplicating project. And that is pretty trivial to implement. You don't need to do anything other than just scan the whole file, throw away the attributes that are not there in the projection list, and just write out the output. Okay, so that's basically trivial to implement. There's nothing more to do. You just want to read the file, drop the other attributes, and just write out a temporary file that contains only the projected attributes. What is the I/O cost? Again, for all these operator implementations, we are excluding the cost of writing out the output as an intermediate file. We are only counting the cost of reading the input and processing the operation. And so the reading for R, the cost is NR, which is the number of pages in R. Okay, so you have to do a full file scan of R on the fly. When you're reading the pages into memory, the processor will just discard the other tuples and then write out the remainder to an output buffer and then flush them to disk in the end. And so the I/O cost for this execution is NR. Is that clear? Now, here's a question. This I/O cost NR assumes that the record layout is a row store. What if your record layout is a column store? Or your page layout? How you pack records onto pages. We talked about row stores and column stores in the file layout and the record layout. If it's a column store, the cost will be much lower than NR. It'll be, I don't know, the size of MID and stars. That's it. The rest of the 3 columns need not be read at all. Because column stores, you pack in a column major order. You only read the pages corresponding to the first 2 columns, these 2 columns that you're projecting on. Okay, so projection in column stores can be much faster than row stores. But for now, all of our operator implementations assume that we are dealing with a row store. The records are packed onto pages in row major order. Okay, now coming to the non-trivial one, which is the deduplicating project. That's the select distinct in SQL. And now here I want the set of unique tuples that have the MID and stars. This is your relational project, that symbol pi. So, okay. The challenge here is in actually doing the deduplication. Because you could have even, I don't know, billions or even hundreds of billions of these entries in the ratings table, this set of projected tuples before deduplication might not fit entirely into memory. Okay, so just writing out MID and stars from R without deduplication, that itself can be very large. So the challenge is actually deduplicating on the entire attribute set, even though the whole set of tuples may not fit in memory. So there are two main approaches to do this deduplication during the project. One is sorting-based, the other is hashing-based. In the sorting-based approach, we start by sorting R on the projection list. So there, we utilize the external merge sort that we talked about earlier. So we see that the sorting is actually being used as part of an operator implementation. What this means is during your sort phase, you basically read the pages from R as you do before, like blocks at a time. And then during the merge phase is when you actually effectively do the deduplication. Now, during the sort phase, as you read the pages from R, you can immediately throw out the attributes that are not in the projection list. So that means the temporary file that you write out after the sort phase is going to be smaller than R itself. So the I/O cost calculation here differs from the I/O cost for the actual external merge sort, because the merge sort doesn't have any projection. It reads all the records with all the attributes, and it writes out all the records with all the attributes. Now, in the merge phase, we saw how sorted runs are going to be compared during the merge process, just like in your merge sort algorithm, with pointers pointing to the records. And when the processor is comparing the entries in these pointers, when it's doing the less than or equal to check, if it detects duplicates, it'll just write out the duplicate value only once. So that is how you're able to do the deduplication during the merge phase of your external merge sort. Okay, so the pointers that you keep in advance during your merge phase for your merge sort algorithm, you can detect duplicates at that stage at no extra cost. So what is the I/O cost? Let T be the temporary table that you write out after step 1. So that's the size of R with the non-projected attributes being discarded. Then the I/O cost is NR to read R, NT to write the temporary file after the sort phase, and the EMS merge phase cost for NT. The EMS merge cost is the same expression you saw in that sorting topic, which has that logarithm of n prime to the base f. N prime here is NT. If you're using replacement sort, then it'll be NT over B, whatever. So that's a whole function expression that I've kind of referenced here. Whatever approach you're using for your external merge sort, all those optimizations, you'll have to factor that in to replace this function over here. Okay, so this is the cost of a sorting-based approach to deduplicating project. Questions? Okay, is that clear? How you're able to throw away the non-projected attributes during the sort phase itself to save on I/O costs by writing out something much smaller than NR. And then during the merge phase, you do the deduplication during the merge when the pointers are compared, and that's basically the EMS merge cost for a temporary file of size NT. Now, how do you estimate NT? Estimating NT basically depends on the sizes of the attributes. If all the attributes are of the same size, then it's just the number of attributes divided by the total number of attributes. Otherwise, you have to count what is the byte width of each attribute and then scale it accordingly to get the size of NT. Okay, the next implementation. Oh, there's a question? No? Okay. The second implementation is a hashing-based implementation, and the basic idea is to build a hash table on the entire projection list as your hashing key. So what is different about this? What is different about this is that your hash table may not fit in memory. You read in your data structures and algorithms class, hash table data structures, I mean, pretty much all programming languages have them, where you can just enter entries and then it'll be deduplicated for you. But the challenge here is that hash table may not fit in memory. If you don't account for how you're paging stuff out to secondary storage, you will end up doing a lot of random IOs. You will thrash. And so your implementation will be super slow. So the goal of hashing-based project is to avoid that sort of a situation where you're doing a lot of thrashing. OK, so how does this work? We again read R, discard the other attributes as and when you keep reading the pages into memory, and then see if you can fit the kind of subset, the table T, which contains only the attributes in the projection list, entirely into memory. If you can, you're in luck. You're done. You don't need to do anything else. You have an in-memory hash table data structure into which you're populating R after discarding the other attributes. And so the I/O cost is just one file scan of R, which is just NR. Okay, is that clear? So if your hash table can fit in memory, this is no different, not that different from your hash table data structures in Java or Python or whatever. However, if the hash table doesn't fit in memory, then what do you do? For that, we need to understand what is the size of the hash table. Okay, so if I give you a file of some size and I want to build a hash table on that file, what is the size of the hash table? And then you have to compare against how many buffer pages do I have? Does the hash table fit onto that? And so what is the size of a hash table on a, say, p-page file? Because we are using extendable hashing index typically, you could also use a static hash index, but typically extendable hash index is used. To count for the hash table size, you have to account for what is called the fudge factor. The fudge factor accounts for overheads, and this is just kind of an implementation convenience that database system people have adopted. Actual size can differ. It can be a little bit lower, it can be a little bit higher, but for convenience sake, we say on average it's going to be a fudge factor size. Okay, so the fudge factor F is about 1.4, factoring in some extra space for overheads on top of the p-page file that you're storing in the hash table. So the size of a hash table on a p-page file is F times p, where F is roughly 1.4. Okay? Given this, the constraint for the hash table to fit entirely in memory is B, which is the number of buffer pages you're given for executing the project, should be greater than or equal to F times NR. Actually, technically, that should be NT, which is the temporary file with only the projection. That's a typo. Okay, so B should be greater than or equal to FNT. Is that clear? Any questions? Okay, what happens if that's not the case? What if your buffer memory is less than FNT? Then you have to do a two-phase algorithm, and that's what we're going to talk about next. And before I forget, let me double check this. This is NT. Okay, I'll update this on the slides. Okay. Any questions about the hash table calculation and when you can actually get away with just one read of R to compute the projection? Okay, great. So what is this two-phase algorithm? We have a hashing, we have a partition phase and a deduplication phase. The partition phase works as follows. Here's your buffer memory. You have B pages, and let's say this is the file on disk, original R. It's the same disk. I'm just showing it on the other side for convenience. You read R one page at a time as a sequential scan. You have one input buffer frame. The rest, B minus 1, are used for basically hashing the records of the input on the projection list. Okay, so given the projection list, you ignore all the other attributes in the record and then copy the records with the projection list value onto one of these B minus 1 pages based on a given hash function h1. Okay, so the hash function h1 takes as input the entire set of attributes in the projection list. Now, you keep copying these records onto these pages. As and when one of these pages fill up, you write them to disk. If this page fills up, you write it to disk. And so what you have ended up doing is partitioning the intermediate file T into B minus 1 smaller files. Now, these B minus 1 smaller files effectively are informed by the value of the projection list attributes that you feed to the hash function h1. Next comes the deduplication phase. You have split up T into B minus 1 smaller files. Let's call them, I don't know, T1, T2, all the way to TB minus 1. And now comes the deduplication phase. Read a partition of T. Let's say this is T1. Read it into memory. Apply a hash function h2 to construct an in-memory hash table for this partition Ti. Okay, so because this partition Ti is much smaller than T, it is highly likely that this in-memory hash table on Ti fits entirely. This hash table on Ti fits entirely in memory. And so all you need is one frame for input buffer to stream this partition in to memory, 1 frame for the output buffer, and any of the remaining pages you can use for the hash table. As and when these records come in, you hash with H2, put it into your hash table data structure. Once the whole partition has been seen, what this hash table contains is the deduplicated set of records for the projection list. So now you can just stream it out to the output buffer, and that basically means you have deduplicated the partition Ti. You can repeat this for every other I. So start with T1, deduplicate T1. Start with T2, so go to T2, deduplicate T2. And do this all the way till the last partition of T is deduplicated. This means the entire file T has been deduplicated. The algorithm is correct. Why? Anything that has duplicate values of the projection list is guaranteed to end up in the same partition Ti. You cannot have records across these partitions having the same value of the projection list. That is what this hash function H1 guarantees. And so any duplicates that arise are guaranteed to arise within the partition. Okay? So that's why you have to deduplicate at the partition level, and you write out the deduplicated partition. The union of all the deduplicated partitions is your deduplicated file. Okay, so this is why this two-phase algorithm is correct. This first partition phase uses a different hash function to split up the file. The second hash function is used for doing this in-memory hash table to deduplicate within a partition. Okay, so that's why it's called a partition. A set partition means there is no overlap among the subsets. Questions? Is this clear, how this two-phase algorithm works? So now, even if your intermediate file T is very large and the hash table on T is much, much larger than the buffer memory B, you have already split this up into almost B smaller chunks. And so that means this partition size could be dramatically smaller, and so a hash table on that is almost always going to fit in memory. So to do that calculation, we have to know what is the size of the partition Ti. Let's assume H1 uniformly splits all the incoming records into these B-1 partitions. So the size of Ti is going to be NT over B-1. So the size of a hash table on this temporary partition file is F times NT over B-1. So that's the fudge factor 1.4 we talked about on the last slide. And so the constraint for the deduplication phase to actually work is B-2 should be greater than or equal to F times NT over B-1. This is the B-2 pages you're using for the hash table. You should have at least as many buffer pages for the hash table on this partition to fit in memory. Okay, so that's how you get the calculation B-2 greater than or equal to FNT over B-1 for this whole two-phase algorithm to work. If you switch B over here, roughly this becomes B greater than square root of FNT. Okay, so NT is the number of pages in the temporary file after you throw out the non-projection list attributes without deduplication. F is the fudge factor, and now you're taking the square root of that. And so that is a very strong kind of reduction. It's square root of NT. So even if NT is in the millions, the square root will bring it down to the thousands. Okay, that's a dramatic reduction, and all you need is that many buffer pages for this two-phase algorithm to work and give you the final result. Is this clear? How we got this calculation on this constraint of the amount of buffer memory available for this whole process to work seamlessly. What is the I/O cost? Assuming this is the buffer memory constraint that is satisfied, NR for reading the file, NT for writing the partitions, NT for reading the partitions. We are not counting the output write cost, because regardless of what you're doing, the output write cost is the same. NR plus NT is the I/O cost of this two-phase hashing-based project. Compare this with the sorting-based project, which was NR plus NT plus EMS merge of NT. Okay, so EMS merge of NT could be larger than just NT. It could be 2NT, it could be 3NT. Okay, so then this can be potentially smaller than the sorting-based project. Okay. Now the question then becomes, what happens if your B is smaller than this constraint? You have NT being humongously large and you don't have enough buffer memory, or at least the DBMS is not allocating enough buffer memory for the project operator to work from its buffer pool, and B ends up becoming less than square root of NT. If that is the case, you cannot do this operation in just these two phases. You have to apply recursion. How are you going to apply recursion? Write out this partition to H1, read each one of these partitions, apply a second hash function, say let's call that H1 prime, and then write out subpartitions of the partitions. Okay, so T is now first split into B minus 1 kind of B minus 1 smaller files. Now you apply a second hash function H1 prime, which is different from this one, to T1, and then split it into T11, T12 to T1B minus 1. And then you split T2 into T21, T22 to T2B minus 1. And so you end up getting, essentially, B minus 1 squared partitions of T. That means you have split up file T into a huge number of small partitions. At that stage, it's almost always the case that that subpartition of a partition of T will fit in memory as a hash table. So that one step of recursion, all you need is NR and T, and then to recurse the partition phase, you read NT again, and you write out NT again. So the recursive step basically increases this IO cost by 2NT. Okay, so that's how you do a hashing-based project. And if this buffer memory constraint, with modern buffer memories, this is almost always going to be satisfied. But if you end up happening to apply a project on an ultra-large file, and this buffer memory constraint is not satisfied, you can do one recursive step, and it'll almost surely be satisfied. If it's still not satisfied, do another recursive step, and then you will get B minus 1 to the 3 number of partitions. And at that stage, basically everything will fit in memory for each of those sub-partitions. Okay, so then, again, you have to add another 2NT for the second recursive step. As many recursive steps as you need, the IO cost will go up by NT for writing, NT for reading. But in most cases, you will just end up with this two-phase algorithm because B will usually be greater than square root of f and t, and this will be the IO cost. Okay, is that clear? Any questions? Yes?
So let's imagine that we have like a result set that's just a bunch of duplicates that
Okay. Hold that thought. Next slide. Duplicates. Any other question? Is this clear how this algorithm works? Okay. Let's compare these two algorithms on their pros and cons. We have a sorting-based project and a hashing-based project. The IO cost, surprisingly, ends up being the same because EMS merge with NT with modern memory sizes is usually just one read. Recall from the external merge sort topic, we did this tabulation. You can sort 70 terabyte file with just under a gig of memory with just two passes, one for sort, one for read, one for merge, but that means merge is just one pass. Okay, so the sorting-based project can actually match the cost of the hashing-based project in most cases. However, the sorting-based project has another advantage. The output is in sorted order of NT. The temporary file that you write out after the project is in increasing order or decreasing order of the projection list values. The hashing-based project scrambles the order. It could be in any order. Why is that useful? We'll talk about query processing later. Project is just one operator in your query. Your query might have many other operators in this data flow DAG, the query plan that we talked about. Having a temporary output in sorted order could benefit a downstream operator. Okay, so this is a consideration that the query optimizer has to take into account. In the original query optimization paper, these are called interesting orderings, if you're interested. The last one is the IO cost for the hashing-based project could actually be higher than just NR plus 2NT. Part of the reason is queues. Another reason is duplicates. So what this ends up resulting in practice is sorting-based project is usually the more popular one for project implementation. Okay, now coming back to your question, duplicates. What happens if you have duplicates in one of the partitions of T such that the hash table doesn't fit in memory? What can you do? Was that your question? Yes, I figured. Why don't you answer it? What do you think we can do?
after a certain number of times, you just fail over the sorting phase.
Right. Well, if you know that all the entries are duplicates, you can actually ignore that whole partition. Because project wants deduplication, right? At some point, you will end up with a hash function that sends every projection list value to its own bucket. And so now if you have a lot of duplicates of that value, no matter what hash function you apply, it'll all be hashing to the same thing. So you can actually catch that and say that, okay, this is all duplicates of the same value. I can ignore that from now on. I just need one record from that. But that requires kind of a more sophisticated implementation for the projection, hashing-based projection. That sort of leads to more implementation complexity, and so that's why falling back on sorting-based project is a better idea. It just keeps your system much simpler rather than having to reason about, oh, is this partition full of the same values? Okay? Any other questions? Okay. Now, the sorting and the hashing-based projects are two ways to implement the project operator. However, if you have an index structure on your database, on the file that you're trying to do a projection on, and that index happens to be satisfying certain conditions, you can actually use the index structure to execute the project as well. In the first case that can happen is when the projection list is a subset of the index key. Okay, so you can have a B+tree index or a hash index, doesn't matter. The index key is just a set of our attributes for the hash index or a sequence of attributes for the B+tree index. If the projection list, the attributes you're projecting on, happen to be a subset of the index key, then you know for sure that all the values of the projection list appear at the leaf level of the tree or the bucket pages of the hash index. What this means is you can skip the data file altogether, just go to the leaf level of the tree or the bucket pages of the hash index, use that as your intermediate file T for your sorting or hashing. So the sort-based project skips the data file, takes the leaf level or the bucket pages and does the sorting there, and does the merging and deduplication there. The hash-based project, you read that directly instead of reading NR. Typically, the number of leaf pages or the number of bucket pages is going to be much lower than the number of data pages in your file, because the index only contains the record ID and the search key value. Okay, so whereas the data file will contain all the other attributes as well. So this is one way an index structure can help accelerate your project operation by avoiding the need to go to the data file itself to do a file scan. Is this clear? Okay, so this is why indexes come in handy for more than just the select operator. You can actually benefit from an index in some cases if this sort of constraint is satisfied. Sometimes it can be even better if a stronger constraint is satisfied. Let's say we have a B+tree index, and the projection list happens to be a prefix of the index key. That's a stronger condition. But if you're lucky, maybe that condition is satisfied. You happen to have an index structure on the table that you're doing a projection on, and it so happens that the projection list is a prefix of the index key, then you're in luck. The leaf pages are already in sorted order of the projection list. So basically, you're getting a sort-based project for free. All you need to do is go to the leaf level and scan it sequentially, and you're done, because you can just deduplicate them on the fly. The entries are in sorted order of the projection list. All duplicates will upper one after another. Just keep looking for the value to change, and then that's the one you will emit as the output. Okay, so deduplication happens basically for free if you have this condition satisfied, and the I/O cost is as low as it can basically get, because you have to just scan the leaf level for the entries and then deduplicate them on the fly. Whereas here, which is a weaker condition, you have to use that leaf level as the temporary file T and then do an EMS merge on that, or hashing and deduplication on that. That will lead to more I/O cost than just this one, which is just a simple sequential scan of the leaf level. Okay, so the index can help execute your project in at least these two cases. Any other questions about project implementations? And that's a wrap. Next class, we will talk about joins, and you will see that the same kinds of tricks apply for some of these other operators as well. Thank you, folks.